Look at Malmquist Productivity Index, and I want to know those of you who have heard about it. Those of you who have heard about Malmquist Productivity. All right. Almost all of you have heard about Malmquist Productivity. So please lower your hands. This, because this is very quick. I'm going to rush through this. An index is a tool that you use to compare something. The word index is a singular noun. Plural is indexes or indices. So whoever uses indexes or indices, they are not lying. Okay. And they are used to compare different sets of data in economics. And the key point is that you are comparing the data over time. They are constructed by a weighted average of a series of data. And when you use an index, it helps you. So we have a lot of indices in the world. Some of them are consumer price index, producer price index, okay, labor cost index, the GDP deflator is an index, the Paasche, the Laspeyres, the Fisher, the Törnqvist, and now the Malmquist. So there are several indices. If you are in the world of indices and you learned it and you enjoyed it, you will not struggle at all when it. Now, this Malmquist index was named after Professor Sten Malmquist. And the index is a bilateral index. Ask me a question. A bilateral index is not multilateral index, it's a bilateral index. So you compare two periods at a time. You compare two periods at a time. And the focus is to evaluate the productivity change. Not just productivity, but the productivity change. And it's very important to bring the change because productivity can be defined as an input and over output, but this is change. That is why we focus on over time. Sometimes some people look at it over two different individual specific factors. So you can look at what has been the change in productivity of Man United between 2010 and 2020. Do you know that there has been a change? Those of you like football. Man United 2010 was not a small, but Man United even in the 2000s was solid. Of late, they are like liquid. So that you can look at the change, but also you can look at the change between two economies. You can look at the change in a group of banks over time, or you can look at a change in a group of foreign banks as compared to domestic banks. So in this case, you are not looking at their performance over time, but they are looking at the performance of two different companies over time. So you're not looking at the performance of one particular industry over time, but you're looking at the performance of two different industries compared to each other over time. So Malmquist can look at time periods or individuals. It's a dynamic performance assessment. So sometimes you'll be using the word dynamic productivity. Dynamic productivity is a dynamic performance. So rather than looking at a snapshot of performance like we have been doing, technical efficiency snapshot at one specific point in time. When we were looking at the technical efficiency all throughout, or the cost efficiency, we did not bring time into the picture. We didn't say that, we are looking at the cost efficiency of DMUA at time this. No, we didn't bring time. So if DMUA appears in 2000 or 2001 or 2002, we were lumping it all together and looking at them separately. Are you with me? So that is dynamic performance. So for this course, we are going to, for this research, we are going to just look at Malmquist, okay? Not the global Malmquist, not a Metafrontier. We are looking at just the Malmquist. If the need arises for any one of you, we'll be looking at those other ones. One of you is looking at multi-directional efficiency. That person might be slightly interested in the global. Here is the history, a quick history about the two. Shepard, 1953, and Malmquist, they pioneered this whole distance function idea in the world of economics. When we talk about distance function, and I want you to pay attention here, you can use it to define a lot of index numbers. Those index numbers I spoke about earlier, all of them, even including the Hicks-Moorsteen, all of them, you can measure them using distance functions. And so you will see that we'll be using distance functions a lot. But already you know what distance function is, don't you? The distance function is a reciprocal of what?
Technical efficiency.
So it's a reciprocal of the technical efficiency. So don't be lost. Under the inspiration, and this history, sometimes you have to bring it if you are doing Malmquist in a different way, so that it will not be tautological. The one that inspired the Malmquist was the Malmquist index was Malmquist and Shepard. But the one who brought it into productivity estimations is Caves. There were three people: Caves, Christensen, and Diewert. That's why it's known as CCD. Caves, Christensen, and Diewert. These three guys, they were the ones that introduced the Malmquist. But they defined it in terms of distance functions, not in terms of linear programming and technical efficiency. And we know already that DEA has been established by Charles Cooper and Rose in 1978. And Charles Cooper and Rose have shown how Farrell data-based activity analysis can be solved using linear programming. So Charles Cooper and Rose were the ones that connected the Farrell approach in the world of linear programming. Now, Fair, Groskopf, Lengren, and Roots, 1992, they combined the ideas of Caves 1982 and CCR idea of 1978. Okay, so they are using the activity analysis, okay, together with the index numbers ideas, and they created the Malmquist Productivity Index. Initially, FGLR, 1992, they created the approach. But then, Fair, Groskopf, Norris, and Zahn, they expanded it, they decomposed it even further. And they connected the Farrell idea, the CCR idea, and the CCD idea, and they created the Malmquist Productivity Index. Or some best way, Malmquist Productivity Change Index. This is a bit of history. And it is good you know all of these references. They are in top job, because these papers are, some of them are, especially this FJNZ, is in American Economic Review. So they are in top journals. Malmquist defined the quantity index as ratios. He used the idea of indifference curves, and he worked on consumer theory. But these guys, the Caves, Christensen, and Diewert, they substituted the technology frontier for the indifference approach. And so they defined a productivity index in the spirit of a consumer theory by Malmquist. This history is good if you are really, really learning well. There are two kinds of surveys of this Malmquist index. One is by 2004. This is directed to operational research audience. And Fair et al. 2008, we call it the Red Book. Do you all know the Red Book? Who knows the Red Book? This one is designed for economists. If you don't know the Red Book, please get a Red Book. Ask in the group page, you get it. Okay, get a Red Book, because the Red Book is the master of it. Nobody passes through a proper, thesis writing without reading the Red Book in this area. So get a Red Book. It's by Fair and Tal, the 2008. Now, this bit of history is also very important. In 1982, somebody, Nishimizu and Page, had already introduced the Malmquist in the parametric framework, in the stochastic analysis. We've already mentioned this. This is where they use a lot of distributional assumptions, and you have to specify functional forms and all of that. 10 years later, Fair, Groskopf, Lindgren, and Roos introduced it in a non-parametric DEA approach, which is what we just said. But we said that their own, remember, Fair was there, and in the second 2 years later, Fair again came. Groskopf again was there, husband and wife, by the way. Lindgren and Roos were not there, substituted by Norris and Zhang. They extended the original Malmquist, and they decomposed it into 3. Unlike the previous one that did it into 2. They decomposed it into pure efficiency change, scale change, and technological change under both CRS and VRS. So the difference between the two is a little bit of an extension. 2 different versions of the Malmquist are there, but we are going to focus on only the adjacent. The base period by Berg, Fossand, and Jensen. Those in the Scandinavian guys, they like that. But we're going to focus on the adjacent Malmquist. Adjacent here means that you can compare 2 periods. So you can compare 2000 and 2001, 2001 and 2002, 2002 and 2003. But you can also compare 2001 and 2005, or 2005 and 2007, or 2008 and 2001. You can compare any 2 periods. But in the Berg, Fossand, and Janssen one, normally you only compare all of them to one particular year. So you are comparing 2010 with 2000, 2011 with 2000, 2009 with 2000, 2004 with 2000, 2009 with 2000. Everybody's being compared to 2000. That is when you deal with the base period, and we are not looking at that. These are the different extensions of the Malmquist. Ray and Desley, again, in American Economic Review, added a scale decomposition. Remember, I told you that these guys, if you look at them carefully, okay, here, they did pure efficiency change, scale change, technological change. But Ray and Desley came and indicated that that scale part is not that nice. So they adjusted it a little bit. Shestalova created something we call sequential Malmquist. Pastor and Lavelle brought the global Malmquist. Asmal and Tam created a global frontier shift. Lavelle created a Biennial Malmquist. It is possible, highly possible, that those of you doing pure productivity change, some of you will do the Biennial Malmquist, so take note. Oh, Shen and Yang created a Metafrontier Malmquist. Remember, the Metafrontier was one of the things I said we will not do. Okay. And then Afsharian and Ann created the overall Malmquist. We are looking at the original one, okay, and it's a few adjustments, and then potentially the Biennial Malmquist, the Biennial Malmquist, the Biennial Malmquist. Now, why did they use DEA to estimate the Malmquist? Because DEA has some advantages, can handle multiple inputs and multiple outputs with few assumptions without information on input and output prices. Okay? DEA can decompose productivity change into efficiency change, technical change, or technological change. Please know the technical change can also be called the technological change. We will look at the details of this. Okay. So if you can decompose the thing, it means that it's helping you to find the sources of productivity. And you can also look at trends and patterns in the industry and make policies. These are some of your reasons. And every time you are using a methodology, you got to justify why you are using that particular methodology. And these are some of the reasons. And your thesis reader must know that your justification. So don't just go and say, I'm using the thing. Justify it, write it in the methodology section. Now, this particular examples of estimating, illustrating the Malmquist is a little bit abstract. So I will jump it a little, and I'll come to the actual one later. Okay. So I'm going to show you a different sample data approach of dealing with the Malmquist. Sometimes we are trying to, there have been a lot of disagreement as far as the Malmquist is concerned. I've given you all the references here. the returns to scale assumptions, and all of that. Mixed period efficiency, scalar components, and all of that. We'll talk about. I want to use this example data to explain it, and I will refer to some of these disagreements and all of these estimations as time goes on. Okay, I want to estimate, use this data to give you an idea about the market. Please, who can tell me how many DMUs do we have here? How many DMUs do we have?
Doc, 6 DMUs.
No.
Please, 3.
3 DMUs. Exactly. How many time periods?
2.
2 time periods.
2.
2 time periods.
Is this input orientation or output orientation, and why? Please now raise your hands. It helps me so that we don't have a lot of communications. Is this input orientation or output orientation? Be raising your hands for me. Input orientation or output orientation? Yes, Dinah. And why?
Doc, input orientation. Because we have 2 inputs and the output has been normalized.
That what?
2 inputs and the output has been normalized. It means that the concentration is on the inputs.
Okay. Do you all get it?
Yes, please.
Yes, please.
Now, how do we know that we have 2 time periods? You can tell me. How do we know that we have 2 time periods? You can tell me. Yes, Tama.
Because you have A1, which might represent time period A, then we up to C1, then we have A2, which represents time period M2 up to C2.
Okay, please say that again.
So we have A1 to C1, which represent time period 1. Then we have A2 to C2, which represent time period 2.
Perfect. Very good. Now, I am using 3 DMUs, but please, whenever you are doing this thing on your own, I need a minimum of 6 DMUs. So you should always have 6 to 10 DMUs. Now, if it is 10 DMUs, it means you're going to have 20 observations. Okay. I don't want it too simple like that. I want it a little bit plenty so that you can have several, examples. So use 6 to 10 DMUs when you are creating your hypothetical data set. All that is said are indicated here. So the frontier technology in period 1 is made up of A1, B1. Now watch that word, the frontier technology. The frontier technology. And of course, the frontier technology for period 2 is A2, B2, C2. Now, I'm going to plot the data set. I've plotted the DMU A1, C1, and B1. That is what I've plotted there. Do you see them in red?
Yes, please.
Yes, sir.
All right. A1, C1. And of course, when it comes to this plotting, I'm sure you guys can do it. Everybody can do it. Is that not so? Everyone can do it. Now, you should also plot the A2, B2, C2. Now, I have plotted it, but it's not obvious. Do you guys see that?
Yes, please.
Okay, explain why you said yes, please.
I can see there's 2 boxes that are not filled. One of them is, I think it's 2 and 3. and the other one is at 3 and 1.
Say that again.
I'm saying that there are two, I can see two boxes that have been plotted. So one of them is at 0.23 and the other one is at 0.31.
Good. So you can see that it's kind of gray, isn't it? It's sort of.
Yes, please.
It's sort of gray. So that's the key one. That's the key thing, which shows that. But then I'm going to use just the year one as a starting point. That's what I'm going to use to deal with it. Now, can I join the frontier? Absolutely, because you have A1 and B1. And this is an input-oriented framework. So I can join this one to that here, and then create the free disposal line. Okay. I can join that to that and create a free disposal line. This is what I've just done here. So I've created a free disposal line, stretching this one and stretching the upper. And then I've drawn the radial, fashion. That's what you see. Now I've added a second one, which is the A2. The A2 happens to be at the same point as the A1. How do we know? Well, you know that by looking at the value. Look at A1. It is 1 and 3. Look at A2. It is 1 and 3. So they are all meeting at the same point. That is why you can see the situation here. Now pay attention. You will have to do your own plotting, your own frontier, your own radial line, and your own labeling. You have to remember that a frontier 1 in this case is the blue frontier. Now, how do you estimate? The first thing you want to do in this thing is to estimate the efficiency scores of every observation, not every DMU, because a DMU appears twice in this case. In your thesis, it will appear maybe multiple times, 10 years, 5 years, 20 years. And when you have a DMU that appears twice like that, we call the first one observation, and we call the second one to observation. So we are dealing with observations. We are not dealing with just DMUs. So what I want you to do is to calculate the efficiency score of all these firms. Sorry, of all these observations. See, I almost made a mistake. Okay. So calculate, you read it on the axis, either the left axis or the right axis. So calculate, but yes, so calculate the efficiency score. These efficiency scores you are calculating, they are called own period efficiency scores. Own period efficiency scores. Own period efficiency scores. Now, why own period? Well, look at A1 in blue, A1. You are going to measure the efficiency of A1 relative to the frontier 1. That's why it's called own, because A1 is in frontier, the technology 1. So you're going to measure the efficiencies of A1 relative to the frontier 1. That is why it is own period. And when you are estimating the efficiency score of A2, it is going to be relative to frontier 2. So that is also own period efficiency score. When you are estimating the efficiency score of C1, it is relative to frontier 1 here. And when you are estimating the efficiency score of C2, it is relative to the green frontier, which you read here. Now, of course, you don't see the numbers, do you? So whenever you are estimating, I will show you the numbers. Where is the graph? Okay. This is it. These graphs, I have brought grid lines. So the grid lines will help you in the estimation. When you are lost at any point in time, you're not exactly sure of the value, please let me know. Then I'll give you the exact value. But I will ask you, what do you think is supposed to have been the value? Then I'll give you the exact value so that we'll have a correct number of answers. Own period efficiency scores. So start. If you are lost at any point, let me know. So do the own period efficiency score for all 6 observations. Who is finished? Who is done? Okay, Yao Apo, you are done. Chris Akotia, you are done. Emmanuel Edu, can you tell me for each one of them? And remember, we are talking about theta, technical efficiency scores. Okay, so you have to say theta A1, theta A2, theta blah blah, theta blah blah. Okay, so start.
Theta A1 is equal to 1. Theta B1 is also 1. Theta C1 is 0.77. Theta A2 is equal to 1. Theta B2 is also equal to 1. And theta C2 is 0.8.
Okay, who has different answers? Lower your hand if you don't have a different answers. Okay. Yes, Chris.
Doc, I'm trying to lower down the mistake, sorry.
All right. Okay. All right. So the way you estimate efficiency scores were clear for all of you. Now I want to show you something. Okay, these efficiency scores are called own period efficiency scores. Okay. And you have to know how you define them. This is it. Did you get all of these? You didn't get the C1 exactly as it's supposed to be, right? What did you get for the C1?
Yes, Doc.
What did you get?
I got 0.77. 0.77.
Because you use what value?
I use 2.3. Just 2.3.
Okay. But you know how I got a 2.333? Because I let the software guide me, first of all, but it's good. It's good. So watch the way you have to write the efficiency scores. Watch the way you have to write efficiency scores. And that is how you estimate it. All of these are called own period technical efficiency scores. But you see, if you look at them, and this is how we read it. This is read as the efficiency of observation A1 relative to frontier 1. Frontier 1. Frontier 1. But what you are seeing here is if I'm calculating the efficiency of A2 is relative to frontier 2, frontier 2, frontier 2. So that is own period efficiency scores. But then there's another efficiency score which is called cross period or mixed period efficiency scores. I'm going to do an example for you. Cross period or mixed period. Now listen, you're going to do for each one of them. So for observation A1, you are going to estimate the efficiency score of A1, but relative to frontier 2. Now you got to be careful when you're doing these things because some of them will be behind the frontier, and I'll talk about it. So if you are estimating the efficiency of A1, A1 is here, but relative to frontier 2 also happens to be here. Let's take something like C1. If I am estimating the efficiency score of C1 is right here at number 3. Okay, so that it will be, if it is efficiency, it's going to be the distance to the frontier divided by the distance to the fan. That's how we normally estimate it. But in this case, C1 is in the technology set 1. So if you are estimating the efficiency of C1, it has to be the distance to which frontier? The green frontier, which is frontier 2. Right? Which is what value?
2.
And then relative to the distance to the frontier itself, which is what you get here. Now, remember that these estimations, you are picking them on the x-axis. You can also pick them on the y-axis. Always remember that. Always remember that. So you got to estimate the efficiency of A1 relative to frontier 2, A1 relative to frontier 2, B1 relative to frontier 2, C1 relative to frontier 2. Then when you are done, you do A2 relative to frontier 1, B2 relative to frontier 1, C2 relative to frontier 1. That becomes what is known as cross period. Another name is mixed period. You see, because we are crossing the periods. Cross period, mixed period. Sometimes it's called intertemporal period. So these are the names you get: cross period, mixed periods, and then intertemporal period. So I want you now to start and compute the efficiency score, all the mixed period efficiency scores for me right now. Now, that means that the numbers will not be the same as you can see when we were doing this one. Okay, like 1, 1 at the top, 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 2, 2 at the top. Those are own period. But now it's going to be 1, 2, 1, 2, 2, 1, 2, 1, 2, 1. Do you get what I mean? So start computing it. When you are done, raise your hand. Start computing all the cross period efficiency scores. One particular one will trick you. If you are lost at any point, you let me know. Who is done? Anybody done? Anybody done? Chris Akotia. Daniel Amaibo. Edwin Abini. Diana. Okay. So Daniel, can you walk us through the first one? You have to be clear about telling us which one specifically that you are dealing with. So what I mean by you have to be clear is that if you look at this one, the one in the bracket is relative to frontier 1. And here is B1 relative to frontier 2. So let us know what is in the bracket and what is outside the bracket. Oh, each one of them. Okay, so take us through. Done it.
Okay, so I have theta 2 bracket A1. So A1 relative to frontier 2 to be 1. And then theta 2 B1 0.8. Theta 2 C1 0.66. And then theta 1 A2 1. Theta 1 B2 2. Theta 1 C2 0.875.
0. What?
No, please, I'm done.
The last one is what?
0.8. All right. 0.875.
Did you mention the 2? Did you?
Yes, I did.
All right. So guys, this is how it's supposed to be. Let me just quickly explain. The very last one that is a little bit confusing is the 2. I want to just briefly talk about that one. So you're calculating the efficiency of B2 relative to frontier 1. Okay. B2 is outside that frontier 1. So if you try to find it, if you even stretch the radial line, it will go all the way here and you will not get it down here. So you have to use this axis rather. So B2 is actually on number 1. If you look at it, B2 is at number 1. And the frontier 1, because this part is going to be horizontal, horizontal, horizontal. If you look at it carefully, okay, because it's going to be on the horizontal terrain here, okay. So if B2 is stretched from this section all the way, it will surely go and hit this frontier at the same number, which is what? Number 2. Okay. It will hit it at the number 2. And so the efficiency score is going to be, remember, it's going to be the distance to the frontier divided by the distance to the fen. And the frontier will be here, which is 2. And then the distance to the fen is this B2, which is here. So that will give you 2 over 1. And 2, you can't read it here because you can't know the exact value on this axis. You will know the exact value here, which is 3. But you don't know the exact value here. And that is because you can't stretch it that way. That's why I always say that you have to sometimes read it on the vertical axis or the horizontal axis. So now you have the efficiency score of all the firms, both the own period efficiency scores as well as the cross period efficiency scores. You have all of them there. Who is not clear with something? Let me quickly explain. So these are the mixed period or cross period efficiency. Now, there's something you need to note. And it takes us back. And Diana, you want to understand this because you are going to do the concept of innovators. And I want to read something very important to you guys here.
Okay.
Now, here is the point. The Malmquist should generally be calculated under a constant returns to scale. And by now you all understand constant returns to scale. Even if the true technology is VRs. Now, even if the true technology is VRs. Now, you remember that all of you are going to determine the true technology by the non-parametric test of return to scale by Simard and Wilson 2002. You remember you're all going to do that?
Yes.
Yes, Doc.
Part of your objective, you try to determine the returns to scale underlying the industry. Now, even if the returns to scale underlying the industry is variable returns to scale technology, some people believe that the Malmquist should generally be estimated under CRS. But that is balderdash, because you wouldn't want to estimate Malmquist under CRS when in reality the technology is not CRS, it's VRS. You know, other than that, you are going to make some conclusions based on CRS when in reality the firms are of different sizes. Now, the reason why the people that suggested this reasonably suggested that is because if you don't estimate it under the CRS, the mixed period efficiency scores, the cross period efficiency scores that you guys just calculated, they are only guaranteed to be well-defined under CRS, not under VRS. They are guaranteed to be well-defined. They are guaranteed. Somebody should tell Viscount that he's always interrupting us. Okay. They are guaranteed to be CRS under CRS.
Doc, my destiny is on me.
They are guaranteed to be, you don't need to even come and explain. They are guaranteed to be under CRS instead of under VRS. That is a cross-period efficiency scores. Now, the reason is because some of the efficiency scores, like you saw for B2, it was outside the frontier one, and yet you are estimating it. So it's like it's not even in the technology set of frontier one. And so if you estimate it, it will be outside. So the efficiency score is going to be super efficient. The firm is going to experience super efficient. And that is why the score is 2. Remember, the input-oriented efficiency scores are between 0 and 1. And yet that one was more than 1, which is 2. So that means that the score is not an efficiency score, it's a super efficiency score. And when you get some super efficiency scores, listen carefully, when you get some super efficiency scores like 2 and they are more, some of them will not be defined, well defined. In other words, you will not get their values if you are using the VRS technology. If you are using the CRS technology, fine, good. Because everything will be under the 45-degree line. But if you are using the VRS, because the curve actually bends, because it bends, it's a piecewise linear envelopment, convex envelopment. Because it bends, the possibility of you not getting a score is high. And so that is why these scholars suggested that you should, and Ray and Desley used to talk about this thing, that you should always use the CRS. So that means that there is a problem in estimating the mixed period efficiency scores under VRS. This is the point. There is a problem of infeasibility. Take note of that. There is a problem of linear programming infeasibility when you estimate the cross-period efficiency scores under VRS. Note that point down, bold, underlined. There is a problem of linear programming infeasibility. Infeasibility means that some of the scores will not be obtained. They are unattainable. So even sometimes the software will tell you NA, not available, because you are estimating that particular thing under VRS, and when the score is a super efficiency score and not visible. That has been one major challenge when it comes to estimating cross-period efficiency scores. That is why they suggest that you should always deal with using what? The CRS instead of. However, there is a way you can solve this problem by using the Biennial Malmquist I told you about. So when there are challenges, there will be such challenges like this, the 2 that you see here. When there are potential of these challenges of super efficiency scores, and please note, you got to be super efficient for you to be infeasible, okay, a firm must be a super efficient for that firm to exhibit infeasibility. But not all super efficient firms should exhibit infeasibility. But once you are exhibiting infeasibility, it means you are super efficient. So it is those super efficiency firms that will exhibit this sort of mixed period infeasibility. And this can make you throw some of the DMUs or observations away. In order to avoid that, many people talk about using the Biennial Malmquist. We shall discuss. So here is a fact I've said. Sometimes some of the observations are likely to be located outside some of the frontiers, which is what we just saw. Outside the frontier they are compared to, resulting in the mixed period super efficiency score for input oriented. Remember, for input oriented, because if it is for output oriented, the score will be less than 1 for mixed period infeasibility. Also, some of the observations can have their projection point located on the horizontal or the vertical sections of the boundary when their super efficiency scores are estimated, leading to mixed period infeasibilities. When they are super efficiency scores, that's what you want to know. So you got to be super efficient for you to exhibit mixed period infeasibilities. That's it. Any question on this before I move on? Any question on this? Any question on this? This is important. This point slide here is crucial. Now,
Doc, please. So, are we saying that if, like, in the course of conducting our thesis, our writing, if we conduct the RTS test, and then, for instance, we get VRS as the true technology, if I'm doing cost efficiency and then cost productivity, are we saying that during the cost efficiency level, I'll use the VRS, but when I'm doing the Malmquist, the cost Malmquist, I have to do it under CRS?
It has to be CRS, VRS all through. If the technology set is VRS, you use VRS all through. And I'm saying that there is a way you can solve this problem of mixed period infeasibility. So
Okay,
you will not use the normal Malmquist that we are studying, you will use the Biennial Malmquist in that regard. Oh, and by the way, there is a Biennial cost Malmquist index there.
Oh, okay.
Yes, there is. The same way there is a Biennial Malmquist index there. What we are doing here is normal Malmquist, but there's a Biennial Malmquist, which will solve all of these problems.
Okay, Doc.
But if it tells you that, and you see, mind you, sometimes you can have the VRS, and yet you will not have any mixed period infeasibility problem. You get a point?
Okay.
Yes, it is possible that you will not have any mixed period infeasibility problem. And if you don't get any mixed period infeasibility problem, you don't have any problem. However, some people can say that I don't want to know whether I will get it or I won't get it, so I'm going to go straight ahead and use the Biennial Malmquist.
Okay. Okay.
But the majority of the time, you know, you wouldn't have any of these challenges. But especially you have a number of data sets, many data sets, the likelihood is there.
Okay. Thank you, Doc.
Any other question? It's very important if you're not clear with anything here, you say it. But this will help you. This is it. This is it. Okay, all right. Now, when you have given your examples, then you have to formalize the model. Now you have to formalize, write the mathematical formulation of the model. Biennial, not technical. So now we are, not efficiency, but Malmquist, productivity. So your productivity change, you have to formalize it. So we are now going to formalize. When we say formalizing, what it means is that we are bringing a bit of mathematics into the picture. So let's assume that this is what you will say as well in your thesis, okay? That we are assuming that we are having n DMUs to be assessed in the light of M input and S output. So the number of inputs are M, total inputs are M, total outputs are S. One particular DMU will be called XIJT and YRJT. Remember, I and R are the inputs for the particular DMUJ. And then the XIJ T plus 1, T plus 1, these T plus 1 are the second period. These are the inputs and outputs of the DMU at time periods T and T plus 1, respectively. And then the I has been defined. That is start from 1 all the way to M. The R has been defined as coming from 1 all the way. So these are the total number of outputs. Output 1, 2, 3, up to S. So if the total outputs are 4, then S is 4. And then the total number of DMUs. So the J is the DMUs, and the DMUs number from 1 to N. So if you are dealing with 25 DMUs, then you have N to be 25. And the time period, okay, we sometimes say time period is T equal to 1. I think I didn't bring it, but ideally you can bring it. Okay, time period T is 1 all the way to capital T. Time period T, small t, is equal to 1, comma, dot, 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 comma, capital T to indicate the time period. Are you guys with me with what I just did?
Yes, Doc.
You have to be with me. So T is equal to 1, comma, up to, capital T. This will indicate the time period. So if you have 10 years, then capital T is going to be 10. Okay? So that you're going to have capital T to be 10. So that is the total time period. All right. So this is how you got to formalize it. Then you go ahead and then indicate it. So how do you formalize the own period input-oriented efficiency score? Look at the way I write it. Everything is TTTT, own period. So this is defined as the efficiency of naught, the efficiency of DMU naught relative to frontier T. The efficiency of an evaluated DMU in time period T relative to frontier T as the own period efficiency score. For DMU in time period T can be defined. How do you define the score? This is how you define it. So you say that theta star T into bracket TT, okay, you should minimize theta subject to what we know. In fact, it's the same thing as we know. Watch it. The theta is attached to the X, which is the input orientation situation. Everything is at the technology set is what is on the left-hand side. The only difference is that we now have to the power T, 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 okay, for all of them. So this is the own period efficiency. You have to learn how to write this thing. It's very, very, I remember we have to learn how to write it, close our eyes and write it, close our eyes and write it 10 times until you get every detail correct. Now you have to define your I, which is from 1 to M, your R, which is from 1 to S, your J, which is from 1 to N. This is the standard across all papers. Sometimes some authors want to be complex, but this is the standard and go with the standard. I go with the standard and still publish it in good journals. Now, if it was to be own period for T plus 1, everything would be the same. The only difference would be for T plus 1. Okay. Own period for T plus 1. Now, what I want you to do is how do you use this data set to do the own period efficiency score for C1? For C1. Okay. How do you formulate C1 in connection with this? How do you do that? How do you do that? Well, it's very simple. Okay. You got to understand that C1 is having input of 3 and 3. So it means that the input here is going to be less than or equal to 3 theta. The other one, because the input constraint is going to be 2. Because and the other one is also going to be less than or equal to another 3 theta. Then on this left-hand side is going to be the summation of all the firms in year T. Which year? Year T. So that is all of these firms. Okay. So if it is in year T, you have to make it in year T. going to be comprising these 1, 3, 3, 2, 3, 3, just those ones in your T. Okay, so it's going to be 1 lambda 1, 1 lambda A1, okay, plus 3 lambda B1 plus 3 lambda C1. Okay, then it's going to be less or equal to 3 theta. Then you come to the second one, which is 3 lambda A1, 2 lambda B1, 3 lambda C1, less or equal to 3 theta. Okay. That is ohm period for C1. And then you do the same thing. You don't have to do ohm period for C1, formulate it, and then you go and do ohm period for C1. No, you just have to do one. So I'm just using C1 as an example. You just have to do one as an example. So you choose C. So you're going to do for C1, for C2, and then you do their cross periods. Do you guys understand what I mean?
Yes, please.
So the one I just did, this is it. So theta 1 star into bracket C1 is going to be minimize theta of this subject to 1 lambda A1. 1 lambda, this is for the output constraint first. Okay. That was the input constraint. But the output constraint to be 1 lambda A1, 1 lambda B1, 1 lambda C1. Okay. Less than, no, it should be greater than or equal to 1. And you don't attach theta to it. This is it. Okay, greater or equal to 1, which is the output of the DMU of the observation you are considering, which is C1. So that is what has been done for this one. But the one I did before, these are the two that I did before. And of course, you've not forgotten, if it is VRS constraint you need to bring, then you have to do lambda 1 plus lambda 2 plus lambda 3 should be greater or equal to 0. You know, that is the, should be equal to 1, sorry. That is the VRS constraint. Should be equal to 1. Should be equal to 1 for the VRS constraint. But lambda A1, comma, lambda B1, comma, lambda C1, comma, that will mean that you are bringing the non-negativity constraint, which is this one. But so the fact that I didn't add them, I didn't create the VRS constraint means that I'm assuming that we are dealing with constant to scale. Does it make sense?
Yes, please.
Yes,
So
sir.
can you guys be able to formulate their own period efficiency score formulation? Can you formulate your own period efficiency for C2? That is C in year 2. Can you do that?
Yes, Doc.
Do that. Do that and let me see. Do that and let me see. Do that and let me see. Because, and when you are ready, you raise your hand. I'll make you a co-host, and then you can share your results for us to see. Please, if you are copying from somewhere, don't raise your hand. If you are copying from somewhere and you raise your hand, you are just wasting our time. Who is done?
Doc, please, are we doing under VRS or CRS?
Oh no, maintain the CRs.
Okay, Doc.
Maintain the CRs. Anybody at all has been able to do the formulation? You want to look at this one and copy from this side. But of course, you can do that. Even if I don't see it, you can do it, can't you? Who are those who are confident that they can do it? Okay. Who are those who are confident that they can do it? Daniel and then Dinah. Okay. You are either looking at my own or you are. If you were to do this, okay, and we are talking about DMU C2, so you have to write something like theta star, okay, own period, so it's going to be 2, okay, then into bracket C2, okay, equal to minimize theta 2 C2, okay, and then you are going to do the same thing here will come, so I'm not going to write it. The same thing will come, it won't change, okay, and then this non-negativity constraint will not change as well. What is going to change are the right-hand side values here. They are the ones that are going to change. The one will not change because that's the same value. And so you just have to go to C2. Oh, no.
Oh, the left-hand side will change.
Left-hand side will change, okay? It will change, this will change. And let me just go back. So look at the data here. We rather need this portion of the data. We rather need the bottom section of the data. Okay. Which is 132,313. So this is so I normally call it 132,313. Then you have your less than. And then on the right hand side here is going to be 2 theta and then 2 theta. For
3, the second one is 3 theta.
3 theta for the C2 and for the C2. And then here you're going to have 1 A lambda 2, okay, B lambda 2 plus C lambda 2. And then here you're going to have A lambda 2 again plus B lambda 2 again plus C lambda 2 or lambda C2. And then of course, your non-negativity constraint here is going to be lambda A2, comma, lambda B2, comma, lambda C2, comma. Okay. All should be greater or equal to 0. And that will settle you for this second own period efficiency score. So you have to model. So you've done 2 of them. Remember, the Malmquist can only be calculated having 4 different efficiency scores. So you now have one efficiency score, which is own period, another efficiency score, okay, which is own period. You need 2 more, okay, which are cross period. And the cross period is a little bit tricky, but you can always do it. Okay. Because a cross period, you are not going to have lambda 1 outside with a C1 inside. It's always going to be cross. Okay. So you can do the same thing for C1. It's cross period. Well, the thing that we wrote here, okay, you just pick them and come and drop it here. Okay. Once you pick them and drop it there, then you are now having the cross period. Nothing else changes. The right-hand side here will remain. The right-hand side values are going to remain as it is. But then the information of lambda 2, lambda 2, lambda 2, lambda 2, lambda 2, or lambda A2, B2, C2, A2, B2, C2, A2, B2, C2, A2, they are all coming to move to this side here. Okay. And then that non-negativity constraint that you had for this is going to also move. Okay. So there's no specific difficulty in how you practice. Let me see whether I can show you a typical example. So this is the second one that we did. Okay. For the own period efficiency score. And this is the cross period efficiency score. Okay. Okay. This is how you formulate it. So you can see that in this bracket, you have the efficiency of a DME in time period T relative to T plus I, or T. You can formulate it with, so the T is inside, the T plus I is outside, or T plus 1. And then you can use this one to formulate it. Watch it. So you can see that the same C1, but the frontier is here too. So all of the 2, 2, 2, 2, 2, 2 that we did, they are all here. I told you that this right-hand side will not change. So this is efficiency of C1 relative to frontier 2. And you can see that the frontier 2 will be changing. The whole of the non-negativity constraint that was here will also come. Everything that was on this own period section will come here except the right-hand side. And for the other one too, it will be the same thing except the right. This one will also be the same thing except the right. So that is how you are able to use to calculate the cross period efficiency, which you did in the table and in the graph. Just that this course you are seeing is just picking it from the graph or from the software to indicate that. Once you've done the formulation for one of the DMUs, then you'll be able to now do the final. Now, this is the final point I want to do. Note that although the own period efficiency is less than 1, and this own period efficiency is also less than 1, the DMU must be feasible in period T technology. So the own period, the cross period you are seeing here, will have to be less than 1, equal to 1, or greater than 1. Now watch the cross period. The cross period. But the cross period means that you are measuring me relative to a different frontier. So my score can be greater than 1. And that means the firm becomes super efficient. Equal to 1. That means the firm becomes efficient. And less than 1. That means that firm becomes inefficient. Okay. So it can happen that the cross periods can show efficiency, a super efficiency, efficiency, and then inefficiency. So this final sentence said you need four scores to be able to calculate the Malmquist. Now let's go to the Malmquist calculation. And all of these are in the world of efficiency. Note that. This is a Malmquist. The Malmquist calculation, as you can see, you have 2 of own period efficiencies, 2 of cross period efficiencies. And the way you calculate the Malmquist, this is a Malmquist, is the square root of these 4 efficiency scores. Watch carefully, and I need to annotate something. Watch carefully, and you will see that the diagonals, okay, the cross diagonals that you are seeing here, the diagonals are their own period efficiencies. Okay, the diagonals are their own period. You can see that they are all to the power t, 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 and here to the power t plus r, t plus r, t plus r. So the diagonals here are their own period, just for you not to lose sight of what is happening. Because sometimes if you don't take care, you'll be a little bit confused. And then the cross diagonals, okay. Sorry, this is a right diagonals. Okay. From left to right are the cross period, are their own period efficiencies. And then the from the left to right, okay, the upward sloping diagonals are the cross period efficiencies. So you just have to get a trick of remembering them. You just have to get a trick of remembering them. If it was distance function, everything would be reciprocals. Everything will be reciprocals, and there's nothing, no problem with that. Now, this Malmquist can be decomposed into two. Now, this is, so whatever score you get, okay, you get the value of the Malmquist. If you get 2, it means that the productivity is increasing by 100%. I'll explain that very soon. But you can split this Malmquist into 2. And when you split it into 2, you are going to get 2 different things that every DEA researcher. This Malmquist, I told you, is the square root or the reciprocal. Sorry, the geometric mean of the efficiency change. Now, how do we know? If you look at the first part, is efficiency change. Look at it. The things in the bracket is indicating a movement from t plus I, let's say t plus 1, to t. So there's a change in efficiency. There's a change in efficiency. So this is it. This is another change in efficiency. So there is a change in efficiency, efficiency change ratios. Okay. So this first part is the efficiency change measured relative to frontier 1. That is why you have T, T. And this is efficiency relative to frontier 2, T plus I, T plus I. So that is a Malmquist. Finish. But you can split this. Remember the graph, and then remember this. This is interpretation of the score in an input-oriented version. If you get a Malmquist, and this is input-oriented, take note. If you get a Malmquist, and this is input-oriented, please take note. If you get a Malmquist and it's less than 1, less than 1, less than 1, it shows growth. Input-oriented, though. Input-oriented, less than 1 shows growth. Greater than 1 shows decline. Equal to 1 is stagnation. And this is in the software coder. But when you go to the max DEA, the max DEA doesn't want you to be confused. So the max DEA, well, you see, when you tell me that something is less than 1 and it is growth, it doesn't make sense. Okay. So max DEA does some quick adjustment. So the max DEA software will rather tell you that in the input oriented, okay, the growth is greater than 1. So if you are going to use the max DA software, remember that I sorted everything out for you already. Growth, because 1 is greater than 1 is growth. 1 is less than 1, it is decline. And 1 is equal to 1 is stagnation. So this is showing a productivity progress, growth, greater than 1. Malmquist productivity index is greater than 1. It's showing productivity progress. MPI is less than 1. It's showing productivity regress. That's a Malmquist. Okay. So all the scores, we can bring them here because remember, the scores is just the efficiency scores. And we've gotten the efficiency score for DMU-C. Remember, DMU-C was in year 1 and in year 2. This one, we calculated it. We calculated this one. The one on top here, we calculated it. And then we have the scores there. So you just bring the score, 0.778, you put it there. We calculated this cross period. You put it there. You calculated this cross period. You put it there. You calculated this cross period. You take the square root, and then you get this value. 86.07%. Okay. So approximately 86%. I've just converted it to percentage. But remember, we have indicated that in a normal hand computation, the score less than 1 is progress. So this is actually showing progress. But how do you interpret it as progress? Well, look at it carefully. How do you interpret it as progress? You have to bring the number 1 to it. So you take the reciprocal and subtract it from 1. You take the reciprocal. So you take the reciprocal of this answer. But this is what I said max DA does for you. So this answer, take the reciprocal and then subtract 1 from it. When you take the reciprocal of this answer, you will get a number greater than 1. When you subtract 1 from it, you are going to get 0.162, which is 16.2. So what it means is that, okay, so when you take the reciprocal and you subtract 1 from it, you're going to get this value, 1.162. 1.162 simply means that you have the stagnation at 1 and then more has been added. So that means there's a progress. So when you look at this result like this, you will not think it's a progress. So you have to take the reciprocal and subtract 1 from it, which I've done here. And that will be 16. So it means that firm C has progressed by 16.2 between the 2 time period. Firm C has progressed in productivity. Firm C has experienced productivity improvement. Firm C has experienced productivity progress. Firm C is exhibiting 16.2% productivity progress. That's firm C. So firm C. See, when you go back to the story and go and check firm C, if you look at firm C, it is inefficient in year 1. It is also inefficient in year 2 because it's not on either of the frontier. So the firm is inefficient in both firms doesn't mean that it's not progressing. That is why productivity is important, because it tells you that even though they are not really, really efficient currently, they are moving over time towards, a good area. So productivity is augmenting. And so the good thing about productivity, it tells you the pattern, the times, the trends, and the patterns. Okay. So productivity progress is being from year 1 to year 2. Firm C, DMUC. So using this principle, you can calculate the Malmquist for the others. So that if you go and check the Malmquist for Malmquist productivity change for DMU1, it was 1. DMU-A, it was 1. There's no question about that because you can see A didn't move. It was efficient, all right, in year 1 because it was on the frontier. It was also efficient, all right, in year 2 because it's also on the green frontier, but it's not progressed. Now, stagnation means that you're not doing well. You see, that firm is relying on past glory. There are some companies that rely on past glories. They don't do well. They are dependent, because I went to Presec, because I went to Harvard, I'm still good. Relying on past glory, and you're not progressing in life. That is the typical example of firm A. Firm A is efficient in both cases and it's not progressing. So you can't deceive yourself. Oh, I was doing good. You are not comparing yourself with the right people. That is firm A. Stagnation. Stagnation is not good. Somebody says it's neutral. No, stagnation is not good. So when you even bring the bootstrapping into it, it will tell you that the stagnation is not healthy. You want significance. And for you to be significant, you got to progress. Okay. Now look at B. B experienced 58.1% progress. 58.1%. So B is experiencing a lot of progress. Now, why? Look at it from the graph. And the graph always helps you. If you look at B, it was efficient, but it didn't stay where it was in the subsequent year. In the subsequent year, it was driving the frontier. It pushed itself. It was on the frontier. It was on the frontier and it still pushed itself. So B is actually a driver of the frontier. B is an innovator. B is innovating. B is one of those firms who are taking advantage of the technology and innovating, like EcoBank. They are always innovating. B is that kind of a firm. So B is experiencing a lot of progress. So if you want to calculate the innovator, there is a way you can calculate the innovator principle. And there's a formula, there's a calculation. And you will know those firms that are innovators of the industry by taking their scores and then calculating. But for now, these are the Malmquist productivity indices for the 3 firms that we calculate. You can decompose the whole score. I want to wrap up with that, because if I don't decompose, we'll not get to that much time. To eliminate the assumption, the CCD assumption that their own period efficiency score and their own period efficiency score should equal 1, and to allow for technical inefficiency, this guy, Fair and his group, we call it Fair, Groskov, Lengren, and Roos, and then First, Gropos, Norris, and Zahn. These guys, they decompose the Malmquist into 2 components. One is measuring efficiency change, EC, we call it catching up to the frontier. And the other is measuring technological change or innovation. The technological change guys are those who are innovating. Okay. We call them frontier shift. This is a calculation. If you look at this graph, this calculation, you will notice that it is the same formula that has been manipulated to get the efficiency change on the left and then the technical change on the right. At the PhD level, you'll be asked to, one of you can do it though, you'll be asked to find out how we can move from this formula here to this formula. But look at this. This is the efficiency change. This is the own period efficiency for year 1, and this is the own period efficiency for year 2. So you can see that there's a change in efficiency. This will give you the efficiency change. Now, this is attributable to managerial performance. So if this value is greater than 1 in general, what it means is that the managers are improving. Okay? They are improving. They themselves, managerial acumen is increasing. But if this one is positive, it means that the entire industry is doing well. And this particular firm has capitalized on the technological docile. So this technical change or the technological change, if it is greater than 1, okay, remember that is the only one carrying the square root, okay, the zooming. If it is greater than 1, what it means is that the firm, that particular firm, has taken advantage of the industry. You see here, sometimes you go to Presec or you go to Harvard, you might not be that good, but you will take advantage of the environmental conditions in Harvard. Okay? You will take advantage of the technology, of even the name attached to Harvard, and that will make you capitalize on that advantage, and you do well. So in this case, you are not doing well, not because of your own doing, not because of your efficiency, your managerial efficiency, but you are doing well because Harvard is doing well, because Harvard is pushing you, because Harvard is tormenting you and driving you crazy that you got no choice than to learn. And that is the technological change. So the technological, so a firm can be experiencing an efficiency regress, a deterioration in efficiency, but an improvement in technological change, or the other way. So this is where you are doing well, even though your industry is not helping you. So a person can go to a very bad university or bad school, and yet that person will be doing so well because the person has a managerial skill set, even though the entire technology is not doing well, even though the entire industry is not doing well, even though the university is not that strong, this person is so strong. So these are the two, and you can substitute. Remember, the Malmquist is made up of 4 different efficiency scores. So you can take all of these 4 different efficiency scores, substitute them again here into this efficiency change and technical, and boom, 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 you will get the Malmquist this time decomposed into the efficiency change and the technical. So look at the scores here, and always remember that the lower this is input oriented, so the lower the score, the more progress it is. So you can see that the 0.885 is indicating that the technical change or the technological change is driving the productivity of firm C. We got to know that the firm C is experiencing productivity progress. Okay. So where is the progress coming from? It's coming from the technological side more than the efficiency side. So that is good. It helps you to know what is really driving productivity. and we know that productivity is being driven by technical change. So what it means is that firm C is not a good firm, all right, because it's inefficient. But when firm B, the innovator, was innovating, firm C was taking advantage of the technological ambience. Okay, and so it was adapting to the technology and going forward. You know, some firms can do that. They are not that good, but they will take advantage of the environment and then they will thrive. And that was what. And that is exactly what this is an output-oriented computation of the whole thing. And these are the different softwares you can use to compute this Malmquist. So next time we are going to calculate the Malmquist, this time using different software. In fact, basically, we are going to use R. We are also going to use the MaxDA. R and the MaxDA. Any question?
Doc, please, the MaxDA. The one that I got online does not give you access to some of the features.
Oh, but you don't have to use the one online. I have bought MaxDA for the whole.
Okay, so Doc,
I have a full version collected from Venice. Who knows?
Okay, Doc. Thank you.
For your own simple things you guys are doing, you can use the other one. But when you want to learn it on your actual software, you have to go to my office and then you use the one I bought for all of you in the office.
Okay, Doc. Thank you.
Any other question? Any other? We'll not look at the global Malmquist and all of the rest. We'll not look at it. There used to be a software called EMS. Okay, that is the one. That one was good. EMS, you can hold some of the technology and calculate some of this. You can use EMS for that. However, we'll use these two software with the same data set. With this same data set, we use this software and then compute everything